Okay, linear Diophantine equations, it sounds like a scary thing, right? You can tell people today, I learned about linear Diophantine equations. What'd you learn about? It's actually not a complicated idea, and there's a beautiful problem from the book that he starts out with, and this is why I chose Underwood Dudley, because at the end of the day, he keeps it simple. He talks about a corral where there's cowboys and an odd number of horses, and he tells you that there's 20 legs in all. And the question is, how many of those legs belong to the horses? So this is a standard word problem that they get now in 7th grade, except the 7th grade or 8th grade problem has a nice, neat answer. You would set up H is the number of horses and C is the number of cowboys. Remember the nickel and dime problems? Like they tell you how much money there is and you set up a system of equations similar to that. And you'll get an equation 4H plus 2C equals 20. Unlike the nickel and dime problems, you don't get two equations. So there's an infinite number of solutions to this. But the problem is you're only interested in integer solutions. So this actually makes the problem harder. Question? Because a horse has 4 legs. So you're counting up the total legs. So this is the algebra problem. So same as the nickel and dime. You remember the nickel and dime problems? They tell you that there's someone that has a certain amount, 3 times the number of nickels than that he has dimes, and then they give you some information, then you set up an equation that says, you know, you have a money equation, then you have a coin equation, and you set them all up. It's very similar to this. Does that ring a bell, or is that kind of so long ago that you... So I just plotted this on Maple so you can see it. I'm not going to walk over there. I'm going to use my mouse so that you can see my mouse there. So you're really interested in these integer solutions, and you're actually given another piece of information that there's an odd number of horses. So you're really interested in these integer solutions that land you with the odd number of horses. When you restrict yourself to a set like that, you would think that the problem gets easier, but the problem gets harder. You know, when you are working over the reals, you can use algebra and just solve for your solution, and that's it. You're done. Here, you have to look and think, is there going to even be a solution? And for algebra, you have criteria of when you're going to have a solution. And think about linear algebra. That's all that class was about. Criteria when you are guaranteed to have a solution of a linear system of equations. None of that works if you restrict your set to it being just integers. None of them hold. So whenever you restrict yourself to a set like that, those are called Diophantine equations. And because these are linear, is linear algebra a prereq for this class? I think it's a gateway for all our 400 level classes, right? So you had linear equations, you know what linear equations. Linear is still the same, you're just restricting now to the set of integers. And it was actually, he has history in here too. That's why I like Underwood Dudley too. He kind of meshes in the history. So like this is named for Diophantus, who was the first on record. He put first to use algebra, but I put first on record because how do we know, right? It might have been erased from time. Maybe there was cave paintings with algebra on it and they just got erased from time. We don't know about it. So the first on record to use algebraic notation. There's a famous problem. We're going to watch a video sometime. Some of the students in the past have told me that particular video inspired them to continue on in mathematics. But there's a famous Diophantine equation. X to the n plus y to the n is equal to z to the n. They were restricting this to the integers. And you know that when n is 2, there are integer solutions because this becomes Pythagorean's theorem. And you have these special triangles that you learn about in pre-calc. Right? Is it pre-calc where you learn about these special triangles where there's integer solutions, a 3, 4, 5 triangle? So, right, you remember that. So when n is 2, you can come up with an infinite set of integer solutions that make this equation work. There was a lawyer. Lawyers love mathematics. I have no idea why. We used to have a few of them in our class, in our graduate courses, and they'd send these proofs back, like briefs. Like, no, let's cut back some of that. You know, you don't need to expand so much. But he was a lawyer from Ma, and in the daytime he did his lawyer job, and in nighttime he used to come home and just play around with these type of puzzle problems. And he kept these notebooks, and in the notebooks he had conjectures. one of them was that this equation has no integer solution for n bigger or equal to 3. And he said, well, I have an elegant proof, but I have no space in the margins to write it. You can't use that excuse, by the way. So he passed away, and that problem was open. People resolved all the problems in his notebooks except for that one. So this was called Fermat's last theorem, that there are no integer solutions to this equation for n bigger or equal to 3. And people have tried to solve it. People thought they solved it, and it was an incorrect proof. It just excited people. The more it lay open, the more it excited people. And I think it was open for close to 300 years. And in 1996, Andrew Wiles announced that he had the proof of this theorem. And I put 1996-ish because there was a flaw in his proof, and he was devastated because he had already disclosed that he was working on this open problem, that he had a solution, and if he let the world know, then it opens up to the world that these ideas that he came up with to finish and close it, and they would get the credit for being the one who solved Fermat's last theorem. So it was a huge deal back in 1996-ish, because he had the mistake, and then he corrected the mistake.
I just have a question. Like, if you were know the proof, who would you tell?
So this is really interesting. You're talking about the culture of mathematics, and I'm still housed in the math department. I don't work straight in math anymore, but I'm very biased. I think that mathematicians are a very wonderful group because we always share all that we do. You know, if I get excited about a problem, I'm running over to John Cutler's office. I love this problem. What do you think about this problem? In fact, some of the videos I've already shown. What do you think about this? And so we share things. So what Andrew Wiles wanted to do is work on Fermat's last theorem. But if he shared what he was doing, it gets people so riled up and excited. You know, if we get excited about small problems and we're running across to each other's office, just imagine what kind of excitement a big problem would do. So he did the unthinkable in mathematics. He holed himself up for a period of 7 years in his attic and didn't tell anybody what he was working on. And so people would see him in the math department and go, what's Andrew Wiles been working on? Andrew Wiles at Princeton. So they would wonder why he was not telling. They thought maybe he's not working on anything. He had no big ideas or something. But it was very hard for him to keep secret for that long what he was working on, which in medicine, it's pretty natural that you don't share anything because it's a cutthroat competitive world. But in mathematics, everybody shares. So everybody found this odd for a period of 7 years that someone just didn't share what they were doing. But he did eventually solve Fermat's last theorem, and he got credit for it. And I'm going to one day, when this backpack gets a little smaller, bring you a book. What happens is when someone writes a proof like this, it was 300 pages long or so, so it was very long, and other people start writing nicer proofs so that they look at the proof you wrote and they write nicer ones so that it's accessible. And now it's accessible to graduate students in mathematics. So there's a graduate text called Fermat's last theorem, and the whole book is just the proof of that theorem. That one theorem. You know, you see the levels of, you know, you're in pre-calc and you see your math professor doing these long problems on the board. You're like, oh wow, that's cool, you know, because you're here now today, so you must have thought that was cool. Then you're in Calc 2 and you see them coming up with tricks for integrals, and then you're seeing me in here now. You're seeing me do proofs, and each level there's so much of a level to go up. People are really, really smart. So you just can't imagine that someone can be that patient to work on one problem continuously for that long, that it takes that much space to write up. So when you see these movies like Good Will Hunting, where their proofs are on a little board outside of the room, what kind of fiction is that? That's a total fiction. You know, the real proofs are 300 pages.